No worries. Thanks a lot, Marcus, and thanks everyone for attending. For those that don't know me, my name is Ashley Bagley. I am a part-time PhD researcher based in SERG, so Sports Engineering Research Group. And this afternoon, I'm presenting to you my rationale for my second study to be submitted for ethics. And as a result, I would welcome any questions or feedback regarding either the rationale or the method section. So my previous research, or my first study, focused on the kinetics of the block start, and I found some differences in the force application which may affect subsequent steps, but the changes in the force application did not result in any performance differences. Other previous research that has looked at bench sprinting across different phases of the race agree that the left and the right legs perform different roles, and that these changes increase throughout the bend portion of the race, so between the acceleration and the maximal velocity phase. But some of those increases changes could result in potential injuries. Edouard and colleagues in different research papers looked at injuries that occurred during top-level international indoor and outdoor athletic championships between 2007 and 2018. And although sprinters suffered the most injuries across the disciplines, this included those from both straight lines, so 100 meters, as well as bend sprinters, so 200 and 400. Out of the muscle injuries sustained in male sprinters, more than 3/4 of those affected the lower limbs, and breaking that down, more than half affected the thigh, nearly 20% affected the lower leg, and 10% affected the hip and groin. So we look at injuries in bend runners in general. Beckham and colleagues in 2000 assessed 200 to 3,000 meter bend runners during an indoor season and found that most injuries sustained were site specific. But again, this included both sprinters and middle distance runners. So we don't know specifically what injuries bend sprinters are sustaining, or even how often they are sustaining those injuries. We just know that injuries are being sustained within that category. Hamel and colleagues, so there's a bit of a difference in previous research and findings where some injuries are sustained more in either the left or the right leg. So Hamel and colleagues theorized in middle distance runners that the left leg would incur more injuries due to would occur more injuries because of repeated exposure to stress in the frontal and transverse planes in middle distance runners, whereas Pollock and colleagues in 2016 looked at track and field British athletics, but within their discussion, they specifically stated about bend sprinters and found that they all experienced, bend sprinters compared to middle distance runners experienced less repetitions but at higher intensities, but found that greater plantarous injuries and all complete plantarous ruptures occurred in the right leg. So we know that there are many different causes of injuries, and it's always a very difficult question to answer, but I'm only going to look at muscle activity and strength, and hopefully it will help to identify potential injury mechanisms within bend sprinters. So during sprinting or even bend sprinting, muscles eccentrically contract in the late swing phase to stiffen the joints, absorb impact, and decrease joint loading during the early stance phase. Masteray and colleagues in 2012 looked at fatigue during 400-meter runs and suggested that the increase found in the left leg of the biceps femoris was caused by a high eccentric contraction because the leg is more loaded during shock absorption. However, Filter and colleagues in semi-professional footballers found that the biceps femoris had a greater muscle activity in the right leg, but they were running at a curved radius of 9.15 meters. And it's previously been found that running at tighter radii is compared with an open cutting maneuver rather than the continuous turning during bend sprinting. So again, in previous bend sprinting literature in the acceleration and the maximal velocity phases, high eversion ankle angles of the inside foot and increases in peak outside ankle external rotation have been found. Looking at strength differences across a season, Bagley and colleagues found changes in inversion and eversion ankle strength in bend runners on a 200-meter track, but they didn't measure muscle activity. So we don't know specifically for those whether muscle activity was affected the same as strength. And increases in eversion of the left foot during the stand phase due to the eccentric contraction of inverters may place additional stress on tibialis anterior, and therefore it might be a contributing factor to the onset of plantar fasciitis. So muscle imbalance can exist inherently, or it can develop with repetitive activity, whether that is either between corresponding muscle groups of different extremities or between the opposing agonist and antagonist muscle groups of the same extremity. We've been found that pronounced or extreme weakness in one limb potentially increases the action of other muscles, which could then lead to further muscle injuries. So alterations in strength and muscle activity may contribute to previous reported kinetic, kinematic, and spatial-temporal changes in bend sprinters, which could contribute to an increase in injury risk. So the aim of the study will be twofold. It'll be to investigate differences in the magnitudes and timings of muscle activity between the bend and the straight and between the left and the right legs. And it'll also be to investigate the differences in muscle strength between the left and the right legs. So to do so, 20 male athletes who will all be experienced in bend sprinting and have a 200-meter PB cutoff of 23.5 seconds will be recruited. They'll complete their normal coach-prescribed warm-up, which will include sprints at some maximal velocity, and all the trials will be conducted in the tightest lane, so lane 1, which has a radius of 36.5 meters. Rest will be given between each trial to allow recovery and to reduce the onset of fatigue. And then at the end, athletes will be measured walking 10 meters on the straight. Data collection will take place on a standard 400-meter track, and the straight and the bend trials will all be completed in a counterbalanced order from starting blocks. Athletes will wear their normal spikes to maintain the representativeness of the protocol, and also for them to feel comfortable at sprinting at their maximal velocity. 2 high-speed cameras, one from a front view and one from a side view, will also be used to record the athlete sampling at 200 Hertz. And then the data from the cameras will be synchronized with the EMG data and used for gait detection, where the gait cycle will be divided into 5 phases according to the hip and the knee movement of each leg. So we can start to then really break down the gait cycle and see where the muscle activity is occurring and also the onset of it. So wireless EMG electrodes, similar to the one on the screen, will be used, and 8 different muscles on both legs will be used to measure the muscle activity. CENIUM guidelines will be used for the placement of the electrodes, and they'll be applied by the same researcher each time to reduce the variability. The area of each electrode will be shaved and cleaned with an alcohol swab to reduce the skin impedance. This will help to obtain a good quality signal and enable a better electrical contact between the sensor and the skin. Nyquist's theorem dictates that EMG signals should be sampled at a minimum of 1,000 Hertz, but ideally 2,000, to avoid a loss of information from the signal. More current research studies using EMG are starting to actually use the 2000 hertz, and the sensors that I'll be using can easily cope with this. They'll be filtered using a high pass filter afterwards with the 50 hertz cutoff to minimize extraneous noise and possible movement factors in the low frequency region, and a low pass cutoff to eliminate aliasing and other artifacts in the high frequency region. And root mean square will be used as a measure of the power of the signal, and it there has a clear physical meaning, but it also has the potential to detect signals that could be masked by other filters. So moving on to the assessment of muscle strength, this will be within a week of testing on the track so that there's no changes due to training. And the movement will replicate the actions in bend sprinting by the lower limbs, but also the actions of muscles analyzed using the EMG. Isokinetic, eccentric, and concentric peak torque for each movement will be measured. So they'll also be measured at 2 different velocities, so 6 degrees per second, because slower velocities can reproduce greater concentric forces, and also at 120 degrees per second, which has been shown to be the highest velocity for which subjects could produce maximal force in a safe and painless condition. Participants will be instructed to push or resist the force plate as hard as possible, and motivation and encouragement will be given throughout. So to determine whether there is any differences in both the EMG and the muscle strength, a two-way ANOVA will be used for the muscle activity, so to bend and straight conditions, as well as left and right, and then a one-way ANOVA for the muscle strength. And then a Bonferroni post hoc will be conducted if there are any statistically significant main or interaction effects to show where they are. And then Hedges G will be implemented and relative magnitudes of the effect will be assessed. So having collected the data, I'm hoping they will be able to provide a better understanding of identifying potential injury mechanisms in bench sprinters. And then this can be used to assist better and inform coaches and reduce injury risk to athletes. And then I welcome any questions or feedback about my rationale or methods.
Okay, thanks very much, Ashley. Really nice overview of the methods there of your outcome study. So I'll hand over, I'll open to the floor for questions. Do you have any questions for Ashley? Okay, I've got a quick one. I was just wondering, has there been much work around the use of EMG in such dynamic, potentially sort of high impact events like sprinting? And I just wondered what types of considerations you might need to think about with EMG electrode placement, and obviously the additional mass of the sensor.
Yeah, obviously, like the athletes have to be comfortable wearing the sensors, and certainly with the improvement in technology, these sensors are really light. So they'll go through some trial runs just to make sure that they're used to it. But their coach will also be there, so there's no see any changes within their technique. The electrodes have been used on a few muscles in bend runners and also in high impact sports. But because only 1 or 2 muscles have been analyzed before, it doesn't really show or demonstrate the whole picture. So yeah, as I said, to mitigate it, a coach will be there just to analyze their technique and just make sure that it doesn't differentiate from the normal.
I mean, I was just wondering if you were expecting any potential challenges with data processing, just with the type of potential identifying specific muscles or signals from specific muscles and potential crosstalk and things like that.
Yeah, there's always that potential of crosstalk, and obviously it's difficult to assess beforehand because it's just unable to isometric one muscle without the others. But if we take the potential the necessary recommendations, then we can try and just mitigate those risks as much as possible. But there always going to be a limitation when using EMG electrodes.
Good stuff. Thanks, Ashley. Do you have any final questions from the floor from Ashley? Okay, great stuff. Thanks for your talk this afternoon, Ashley. Very interesting to see those methods that you're looking to apply to bench sprinting. So thanks for that.
No worries. Thank you, Marcus.